Okay, so let's start our exploration of how the cores boot up, and let's again use the QEMU software to emulate 4 cores and see how the code boots up. Now, before we dive into what's on the screen, I just want to set some ground rules as to what this experiment is going to be. Obviously, we are going to boot, multi-core, and multi-core has this added advantage that, not only do you see single core booting up, you also see, multiple cores booting up at once. Now, the thing that I am going to do is demonstrate the MPIDR register, the use of it. And so we have 4 cores here. And what I want to do is only have one CPU move forward with the computation. And I want all others to jump to a location and just, spin, kind of loop essentially infinitely at the same memory location. So the 0th core is here, the 1, 2, 3, they continue to loop. So this is our setup. And so what you'll see is this processor, this core essentially moves forward while the others are stuck, right? And so with this as the background, let's go ahead and take a look at the code. So what I'm going to do is I have this, okay, let me just say, this is where our actual code starts, and the program counter, wherever it is pointing, we are going to put, the code generated as a result of all of this right here, right? So the first instruction that it fetches is this. Now, at this point, an important information for you, or something that you should be mindful of, is when we are reading data, we can use the load and store instructions. So what that means is when we are fetching content to the GPRs from the memory, we can use the load and the store instruction. Load to fetch it, store to send it back to the memory, right? Or go save it in the memory. When we are trying to read the system registers, however, we cannot use these instructions, right? So ARM has provided special instructions called MSR and MRS. And what we do is the MRS will read into our normal GPR register the value of a system register, and the MSR will kind of write into the system register the value of GPR. That is how it works. So MRS and MSR are 2 instructions that you can be mindful of or remember that they are only relevant in terms of system register, and the transfer is between GPR and system registers, right? Okay, so that said, what's happening here is we are reading the MPIDREL1 register into X0. So each CPU now is going to execute, like start their execution from here and execute this instruction. So each one of them in their X0 register is going to save different number, right? Maybe 0, 1, 2, 3, so on and so forth. Now what happens is in the next instruction here, we are ensuring that we only look at the last 2 bits, right? Because 0 to 3, so only 4 possible combinations, so last 2 bits is what we want to look at. And then we are saying, hey, if if you are if this instruction CBZ here is I think it's conditional branch 0. So what it does is it says, hey, check the X0 register, and if it happens to be 0, which means if it happens to be executed on the 0th core, have it jump to this label 1. And the 1F here essentially means look for 1 in the forward direction, right? And similarly, well, we don't have an example for, what do you say? Um, we don't have an example for jump backwards, but had it been 1 above this instruction, we would have said 1B, go backwards. 1F means go forward. So then what the 0th CPU will do again, right, this CPU will do is it will evaluate this instruction and the condition will match. And so it will jump to this location here. And after that, the CPU goes on to executing all of these and then jumps to prompt. And at this, and prompt is like the C function in this case, part of this repository, which we will not bother about. But here something interesting is happening, right? We are saying, hey, um, like load into the register X0 the value of a symbol, stack pointer or stack top, and this happens to be like a number that we are loading into X0. This number comes from linker script. Again, some black magic that we're doing here as part of this repository. But the idea is that a number gets loaded into X0. And this number, as you can see, X0, we are then moving into stack pointer, the SP register. And then after that, we're calling a C function. Right. So the idea was everything above here doesn't require a stack, but just before jumping to C function, we need the stack. So the stack is set here. And whose stack is set? The 0th core, because only the 0th core has moved on. Now, question then is what happens to the other cores, right? So the 0th core here, that has moved on in life and jumped to from the C function and moves forward from there. At this point, what happens to the other core? So every core has executed these two instructions and go about executing the third one, but this evaluates to false, right? Because X0 in this case is set to 1, in this case is set to 2, in this case it's set to 3. So what will happen is in all other cores case, they will not jump to the label 1, but they will just fall down to executing the B dot instruction, right? The B dot instruction. And the B dot instruction essentially means, hey, branch to the same location. And what they'll do is they'll keep spinning at the same location. Same location meaning whatever address of this instruction happens to be, right? And that's how, we have made the 0th core go forward and other cores are stuck here. Now, this is in part the example here, the kind of repository we have here. We only wanted to have one core move forward because we wanted like one CPU to be functional, others to be blocked. So let me now, quickly go ahead and show you this example. So I do make here, everything's already built. So I do make debug, QEMU launches as part of this, and in another terminal, I do make GDB. Right? And as soon as I should get out of the way. So let me get here. Okay, so as I go to the GDB here, you will notice that program counter should point to this, what is it, 40 million, I suppose, 40 with 3 zeros, 4 million or 40 million, whatever, right? 4 with a lot of zeros. And so the program counter is essentially pointing to that number, right? And again, as I mentioned, program counter just started off with pointing to that number. Cool. So what we see here, the 1 through 4 representing different cores. Now 0, 1, 2, 3 represented as IDs 1, 2, 3, 4, right? But the same idea. Now what I'm going to do is, do next. So as you can imagine, the program counter has moved on and we are only, so to speak, tracking thread ID 1 here, which is CPU 1. And let me just, show something else. So as I keep on doing NI, which is next instruction in assembly, I'm commanding GDB to execute one instruction at a time. So it's pointing to this location. And let's just kind of, if I do C now, what it'll do is it'll release, kind of not do next instruction, but it'll say, hey, continue to execute. Right. So once I do C and hit enter, all the cores are now, freely running. And if I now press Control C, the execution is kind of, paused. And now what we see is, again, core 0 is essentially, right here. It's moved on in life, pointing to some C code right here, but all other cores are like still stuck, right? And what I'm now going to do is try and switch to different thread 2, right? And then I'm going to do like an NI there, and it has also moved on in life. And what we see is, uh, right, so the thread 2 is still kind of, stuck. So that's then like, a very high level view as to how the CPUs boot up and the multi-core boot. What I would have uh, appreciated and expected is that, this different CPUs be stuck at different instruction, the B dot, but that I'm somehow not able to demonstrate right now. But hopefully, you take away that, the CPUs would be stuck on B dot while the others, while the main core moves forward. At least that should be clear from here.